Thanks, Phil. So I'm just going to say a few words, then I'm going to invite the people who just spoke this session to come up, and we'll have a discussion like we've done in the last few things. So I just wanted to say a very small number of things, and so we can get into discussion. One thing that I've heard this phrase said by people at many different companies, including Google and IBM. And I'll say a few words about what MapReduce is, but it relates to some of the things that people were talking about. There's this idea of parallelizability, and many of our speakers talked about parallelizability. Parallelizability has been generalized a little bit recently to, there's a kind of idea of online things and stochastic things, where the data can just be flowing at you and you can look at the data sort of asynchronously. And basically all internet technology is based on asynchronous data analysis. So this is MapReduce. So if you don't know what MapReduce, who here knows what MapReduce is? Only this half of the room? Oh, and our Google employee knows what MapReduce is. So this internet search is the classic example of MapReduce. At the map step of MapReduce, you go to every data point on your distributed system. This is like your LHC data that are distributed around the world. You ask a question of each individual data point separately. And then in the reduce step, you take pairwise and you combine the information pairwise. And you can express, this slide explains, you can express internet search this way, where you ask each document, do you contain the word kittens? And then between pairs of documents, you ask which is higher page ranked. And then since you're always doing pairwise comparisons across your network, you only do a logarithmic number of steps to combine all the data. You do log base 2 of the number of data points you had to look at because you're doing all these pairwise steps. So it allows you to search the entire internet in log time. And if you think about, if you do the numbers, that is the only way you can return a search result in reasonable time. Like all of the internet technology, all sort of web-based search things are based on this because the internet is very large, and so there's just no way that you could do this search if you had to do things in a sequential way or had to reconsider the results from one CPU based on results from the other. It's a brilliant thing because though the load on your air conditioner is n log n, the time it takes to return your answer is just log n because you have this huge distributed data center. And there are some problems in astronomy that can be expressed as MapReduce. So one thing is you can take the derivative of your likelihood function in MapReduce. So this is very relevant to us because people have been flashing these numbers like 10 to the 10 stars and 10 to the 15 photometric measurements and things like that on their various slides. There really is going to be a time where we have to actually do a hypothesis test on some large piece of data. And so if you can take derivatives of your likelihood at the location of every data point, so if your likelihood looks like this, it's a product of probabilities, then you can basically compute derivatives of your log likelihoods and pairwise sum them. And you can take a derivative of your likelihood in MapReduce, which means in log n time you get a derivative. That means you can do optimization in MapReduce, which is a very, very valuable thing. So, maybe big data isn't a problem. But big data is a problem for various reasons. One is, in fact, in real problems, the number of parameters you care about grows as fast as your data do. For instance, as you include more and more data sets, you have to include more and more calibration parameters. Or as you get more and more data, your precision requirements go up so your calibration parameters have to be known more precisely or have more freedom. So it's always the case that your problems get bigger as your data get bigger. And the other thing is you can't actually go beyond this optimization. So in the unconference session, I'm going to advertise here. I've proposed that we talk about weak lensing. So there'll be some unconference thing on weak lensing. And this is my description of the weak lensing problem. Omega is cosmological parameters. Those cosmological parameters produce a shear map, which is gamma. And so there's that shear map. Imagine we're a cosmologist. I mean, I'm not really a cosmologist anymore. Is one of these things a pointer? Yeah. I'm not really a cosmologist anymore, but these are the cosmological parameters. They produce a shear map. There's some idea of what galaxies, this is everything Risa's ever done. No, Risa's worked here too. But then now she builds her galaxies. So this is all galaxy formation. That produces a galaxy shape. Galaxy shape is distorted by the shear map. But of course, when you observe this galaxy, you're also getting noise from a noise model. And most astronomical problems have some kind of structure like this, where there's an outrageously complicated thing here which you officially don't care about, and another outrageously complicated thing here which separates your observations from the thing you care about. See, this horrible thing is right in the middle. How do we deal with that right now, that gamma thing there? Right now what we do is we take these and we make a shear correlation function, and we sort of cross this out, and we generate a shear correlation function from this, and then we just compare those summary statistics. And in fact, Risa even talked about that. We always work at this level of summary statistics. There's something wrong with that. We should be marginalizing this thing out. That's hard. That no one knows how to do that. And for this, and Bayesian inference isn't MapReduce. You cannot do full Bayesian inference in MapReduce. And it looks like you can. In fact, when I first heard about MapReduce, I was like, oh my God, we can do Bayesian inference. Because the map step is you compute the individual data likelihood functions. And the reduce step is you product together the functions. So it works. You compute all the functions, then you product together all the functions 2 by 2. And then at the very end, you product in the prior. You're done. You've done Bayesian inference. The problem is you have to product together functions. Not numbers, but functions. And you have to decide up front how you're going to describe those functions with a sampling or with a mixture of Gaussians or something, or a function space. And that function space depends on your posterior answer, what function space you would choose. And so, in fact, you can't independently do this. You have to know at the end what the answer is going to be in order to decide what function space to work in. So you actually cannot do Bayesian inference, though there's a lot of people thinking about this problem. This is a huge problem in machine learning. Somebody will crack, and there are some approximate solutions. There's something called, I've completely forgotten what it's called, where you approximate the posterior as Gaussian, and you work with Gaussian approximation all the way through. Somebody might be able to tell me what that's called. But anyway, there are some approximations to this, but no one can solve this problem. And you might think, well, this is a good reason not to be a Bayesian, but it's not. Frequentists are also doomed because if you want the whole likelihood function, which is how frequentists are supposed to communicate with each other, in fact, Bayesians are also supposed to communicate. Everyone's supposed to communicate with each other by passing forward functions, and functions we really don't know how to deal with. I mentioned marginalization. I won't say anything about that. I want to get through. My approach to all these problems is brute force. And one thing I have to say, I have to recommend very highly for people who are facing problems is talk to your friends in your other departments. I have extremely valuable now collaborations with applied math and computer vision, and of course machine learning. And we've learned a lot through those interactions, and we've been able to get some superpowers along this direction. And I think a lot of the questions that Risa brought up, there are people with superpowers out there who have things to say, and I don't know much about it, but I think we should be talking to those people. I'm not going to talk about my day job. This was mentioned by several people and several of the questioners in the room. The problem is actually worse than you think it is, because as you get more data, you also vastly increase the number of things you're interested in. New questions become answerable, new questions get asked, new classes of things appear, and so there'll be far, and I wrote these slides a while ago, and it's just so amusing that the talks here just completely came in here. We need citizens and we need robots, and we need to turn citizens into, we need to replace citizens with robots. Good. So I wanted to just put on the slide financial reward. In fact, Bloom specifically mentioned that he wants to take an engineering or a resource allocation attitude towards things. That's something I very strongly agree with, and I think we should be thinking about resource allocation. But it's also the case that if you solve these problems, you will actually get rich, because right now the internet world is kind of stuck at problems that can be solved in the MapReduce framework. So if we make progress there and and make new opportunities, oh, somebody's going to get rich. It might not be us. OK, good. These are my questions, so I'm going to invite the speakers up to the front. Let's go. Good. That includes you, Phil. Good. So my questions are, so my first two questions are very me-ocentric. This is what I worry about, and I write polemics on the archive that aren't refereed because no one would ever accept them about these things. So for instance, Risa mentioned this question of the second question here, how do we directly compare theory with data? Do we have to do it through summary statistics? Could we put a simulation inside the MCMC chain? In fact, that has been done in some exoplanet contexts. The known unknowns, Rumsfeld had such a big influence on the astrophysics community. One of my big hobby horses is about data analysis. One thing that Risa mentioned also in data analysis, which is my top question, is like, should we have standards about how data analysis is done? Risa accused the community of sometimes just freezing some parameters and then making two-dimensional plots. And we all know examples of that. Maybe we should develop as a community over the next decade some ideas about what's appropriate and what counts as a successful analysis. I've always said that a proposal should say that you can saturate the Kramer-Rao bound, and if you can't, you don't need more data. Then one thing that came up in a number of contexts, Dominique mentioned this, is our systems need to be flexible, and how can we make them flexible? One thing everyone is interested in, and Dominique mentioned, is that we must write our systems so that they can be parallelized. But even that's a very 2013 thing to say. In 2023, architectures could be different, methods could be different, scientific questions could be different. How can we be flexible about that future? And that's very hard for me to think about it. This is way beyond my expertise. And then the big question that's in everybody's talk, and of course, one of the things I thought was so beautiful about Stuart's talk is that he brought up the issues of ethics a lot. We're working with people, and these are people-centric systems. Computers are tools for people. And Dominique also mentioned that the big cost of our work is human cost, and that's not just that you have to pay them, but you also are taking their time. And one of the things we're very concerned about at NYU these days is how do we train and promote people who play unusual roles? How do we not repeat the mistakes of the Harvard College Observatory of the 1880s? Good. That's my list. I don't have any idea what to do now. Moderate. OK, let's ask an easy question first. How do you think we can make our systems more flexible, and given that we have no idea what the future holds? That's an easy one. Dominique, have you thought about that? Oh, yeah, sorry, we're a little short of mics. Sure I need a chair, too. Oh,
yes, it is. In fact, it's not the easy one, I think. This is not easy. I was thinking, as you were speaking about this cloud approach, which is some kind of paradox, in fact, because in some sense it is introducing much more flexibility, as this kind of approach is supposed to make you you have not to be tied to some given hardware, for instance, and in principle you have a lot of flexibility because your system is designed to be elastic. This is elasticity is a key word, the most important key word in the cloud computing. But on the other hand, it means that the people using cloud have to become experts in systems. Mm-hmm. And so the thing which is really missing in order to be able to use, in principle, infinite amount of resources through the cloud system is to have the piece which is between the user and the hardware, in fact, and the virtual hardware. in order to make this kind of system easily usable by everybody. So I think that in order to ensure this flexibility, people have really to work on this missing piece.
I agree. Actually, that reminds me that this is also related to this question of repeatability and usability. And I think, and Risa, you had things to say. I mean, you said that people are still using this showing this Millennium simulation because it's just there. Do you want to say something about how we could make sure things are more usable and repeatable?
Well, I do think that we need to have standards, or at least agree on, agree on conventions, right? I mean, I think if people keep their data in similar, right now, I mean, 10 different simulation groups keep their data in different formats, and they publish them in different ways or not at all. And, I mean, this IC thing that we're going to unconference about is a solution to a very tiny part of this problem about, how you would actually do the initial conditions in a systematic way. And I think these conversations are happening more and more. I mean, I've been to several conferences over the last few years where people have tried to do this, and there are serious attempts. I mean, YT is a great example of something which now, reads in, data from many simulations and does the analysis in systematic ways. So, I mean, I do think there are real efforts along these lines, but we need to,
So
I
what
think
about
more effort along those lines.
Well, what about? And I can see Josh is ready to say something.
Well, I was going to say, yeah, I think we are heading in the right direction as a community to start thinking about reproducible science. At least, being able to describe your initial conditions so that if somebody really wanted to, they could start from that and keep going. The whole sort of open source science movement that I think David's been, in some sense, leading, of essentially writing papers out in the open. People then also see not just where the data led to, but where your conclusions came from and who actually contributed to those conclusions. There are a couple of examples. I think it hasn't happened yet in astronomy, but there's one I'm aware of in biology, where they basically, as part of their paper, they submitted an Amazon instance with all of the data and all the code that produced all the plots for the data and all the LaTeX, obviously. And somebody could just go download that, and if they didn't believe a single thing in that paper, they could go back from the scratch and basically, build a new version of the paper from scratch and change something and see what happens.
Actually, that idea is interestingly related to the upper questions, because if we're going to go to more serious inference, one of the things that different surveys are going to have to do is share their likelihood functions. So, one of the most amazing things that's happened in cosmology in the last decade is that WMAP and Planck released not just their data, but their likelihood function. So you can put in parameters and assess the likelihood.
I was just going to touch on one challenge that I see in this sort of reproducible science thread here is that data is, again, back to the time domain, data is changing all the time. And so the idea of versioning data is really problematic, especially when you're talking about versioning big data. And the example that I bring up is, if I write a paper about all the Auralari in that part of the sky, because I made a query to LSST on this day, the next day that database will be different. And yes, if it was really important, we could go back and re-engineer the whole database from the first day up to that moment. That's what we hope we'll be able to do. But the reality is that a lot of data that we're going to wind up relying upon will be either so large to move, or it'll be so large that we're just not going to version it. And I think we're coming from that world from Sloan, where you could say, well, that's from data release 7, and then there's data release 8. But again, Sloan was mostly focused on a static sort of view of the universe, and all you're doing is sort of improving your notions of how the universe is, it is. But when you're talking about the time domain, it is something, and then tomorrow it's something else.
That's right.
And I don't have a solution for that, but it's going to be a real problem for us. It's going to be a real problem, I think, fairly universally.
It will be. It will be. Can I change gears? Do you want to say something else on those lines?
Yeah,
Go ahead.
Just very quickly to say that I think that there are some lessons to be learned here from the citizen science community, and the citizen science community is an interesting one because you can try out different models of collaboration and different models of open publication and open collaboration, and they don't have the same kind of hang-ups as we have as professionals in terms of attribution and like how that works. And so I think there's actually a an opportunity to try out different ways of doing this within the open community, not necessarily at the same level as needs to happen in the scientific community, but it's worth giving it a try. The other thing I just wanted to say very quickly is with this idea of standardizing environments and standardizing data, there's been a number of citizen science projects that have tried to crowdsource like code solutions. Like there've been competitions to say, help us fit lensing better, write a better code for that. And one thing they do very well is having a standard test environment and a standard data environment for using people. And there's technologies to definitely help that, which is pretty fun.
So I want to go to people issues because I think, well, I have many questions to ask here, but one thing that's very interesting to me is that it's possible that so I might be wrong about particle physics, but it seems to me that particle physics has sort of more understood as a community that there will be faculty members and publishers and important members of the community who work on computing or work on calorimeters, but who work on very much engineering and technical aspects of the overall scientific process. In astrophysics, we haven't been so good at creating roles, even though we really depend, like LSST depends very strongly on a group of very good engineers, and the scientific responsibility for LSST will really rest on the shoulders of these people who we think of now as being in an engineering role. And how can we incorporate them into the community? How can we make sure that those people are the tenured faculty of the future in astrophysics departments and so on? Yeah, you want to say something, Dominique?
I think it's a very good point. In fact, I am very, very surprised. This is very naive from me, but I'm very surprised to hear that repeatability is a problem. No, I mean that it is an unsolved problem. Because, frankly speaking, I think that if you ask CMS people, for instance, or Atlas people, tomorrow to reproduce their X result with the version of the data, the version of the algorithm that has been used in order to make the first publication, they will be able to do so. Mm-hmm. So for me, that was not a real problem. I mean, it's a solved problem. It's complicated in order to achieve these kind of things. But I think it's done.
Yeah, shall we go in the audience? Yeah, go ahead.
Right, but in particle physics, we have the whole history and infrastructure of national laboratories, which have devoted resources to these things. And
I agree.
we generally...
I agree, and one of the interesting things about LSST is it's looking a little bit like a national lab kind of project in a certain way, but we as a community haven't moved to a national lab way of feeling about things, and maybe we don't want to. I don't know. I'm just worried that we're going to chew up and spit out a bunch of very, very good people on LSST.
Yeah, I mean, just on that last point, one of the problems we've had, I think, in astronomy is that we've mostly been, it's been essentially an unfunded mandate as of late to make sure that, our science is reproducible. But, until very recently, when the agency started waking up and realizing this was something that the taxpayers should at least be asking for, if not demanding, we never thought about it because we never really worried about it. And in some sense, we never really got that burned by it, right? We weren't building such big, expensive projects where, a 5 sigma hump in, one plot is, worth $1 billion. In the past, it's been, I found that RLIRE, and if you want to go look at it again, by all means, take another spectrum of it. I mean, some part of what we've done in the past has been reproducible by the very nature that the sky hasn't gone away. And I think that was one of Sloan's mantras early on was if we lose all the data, what are we going to do? Or maybe it wasn't Sloan. There's another survey I heard where they didn't have a backup of their data. Somebody said, why? They said, the sky is our backup.
That doesn't work so well in the time domain.
Yeah, that doesn't work at all in the time domain. No, so I think it's been, again, it comes down to resources and perceived need of it. We haven't been forced to do it, so it's, until it comes top down and it's a requirement at every proposal level and it's funded to do, we're not going to do it well. It can't be just a few people in this room who say we gotta, carry the torch. It's just not
I
going to
agree.
take off.
I agree. All of these questions require community changes, not just. And part of what we can do in this room is lead by example. But that's about all. We need to do something bigger than that. Stuart, you are our house ethicist.
I have no idea how that happens.
And one of the things I loved about your talk is that it really contained a lot of ethical questions in it, and it's made it very clear to me that your team is thinking a lot about what it means to interact with people and how to treat people well. So and you also fall into this category of astronomer who's in a strange situation academically. So do you want to say something about the?
I mean, I guess we are so focused on it because if we lose that community, we lose all ability to do anything. And so it's ethically good, but it's also kind of selfish as well. We have a reason to be ethically good. I think that's true of the astronomical community as well. I think there's people who are coming up through PhDs just now who take an interest in the engineering side of things or the machine learning side of things, and there isn't a career path really for them to go through. And we treat them as utility sometimes, I think, without really properly recognizing their contribution to these projects. And I think that has to change somehow. I don't know how that changes, but I think that has to change.
That's the problem.
And I think part of that is, right now, if I write a really good piece of software, I can put it up on GitHub, and when I go for a job interview, people will see that good bit of software, see that lots of people have forked that bit of software, are using it, and it's a good thing that's contributing to the community. Right now, if a PhD student writes a pipeline, they may get their name in the paper, but that pipeline and the code itself is never going to contribute to their future employment success. And so I think there needs to be a recognition for not just papers and publications, but tangible pieces of, and I'm not talking about some weird notion of how good they are, I'm talking about a tangible piece of evidence about how much they can contribute to a project with those skills. And I think that's true of the citizen science community. We want to, and having everything in the open so you can go back and just point to the fact that you did something is interesting as well. We were having a conversation last night at the bar about open science and about how open science people worry about, or writing papers in the open, people worry about being beaten to discovery because they're doing more due diligence to make that discovery. But I think if you make your entire process of that open, including in the same way that you make an entire process of writing a piece of code open, you can point to the early place where you said, we thought at this point there was something interesting, but we didn't want to say it was real until we'd done all these other steps. And so I think openness that helps a lot with this problem. I'm not sure.
Yeah, it's a very interesting idea, that openness about development. And one of the things that concerns me about a lot of, say, simulation codes is a lot of simulation codes are closed up, a lot of data analysis pipelines are closed up, and if people are developing out in the open, maybe that is a baby step towards
yeah, and I think it does two things. I think it helps with the reproducibility, but it also helps with attributing credit properly.
We have an audience.
So I have a question that I think this panel will be excellent to address, because it's something that we rarely talk about in our community, but if our data, especially with these huge systems, LSST, et cetera, is going to be truly open and publicly available, what are we going to do about the lack of broadband connectivity? I mean, not just in the US, but worldwide. It's really hard to do LSST science if you're not at a major university. So do you have comments on that, or do people think about this? I don't know.
I don't know. That's a tough one.
Well, I mean, I agree it's a problem. It would be nice if a globally public data set was actually usable by everybody. I think maybe part of the answer comes from what Stuart was saying about providing people with tools. Yes, it will be difficult to stream a lot of LSST imaging data to your home, but if you're provided with a different kind of access to that data set, then maybe you can still make a contribution. And so it seems a good idea to provide a lot of different ways of interacting with the data. Some that will work better in low bandwidth connection areas and some that will work better in others. Another aspect to the LSST analysis that I like is they have this notion of level 3 processing, where you submit code to a data center and have it run there, and you see the results in the science user interface. That model's nice because it means you don't have to have a lot of high connection. You can do the processing at the data center in our own personal small cloud, if you like. Another aspect, nice aspect to that model is that because there's only a limited amount of computing power at the data center, you have to do it by time allocation committee. And so there'd be a competition for time, and anybody could win that competition if they were had sufficiently good ideas and good code to run there. And so I think I like that model very much. I don't see it in all of the big projects, but certainly with LSST, it's nice to have an API like that.
Josh, did you want to?
Well, I was going to kind of weigh in on this
please
question
do.
of reward structures and metrics. You know, the old sort of gamification of academia is citations, right? And we have a new clout score which is called H-index, and so people are trying to optimize a couple of numbers that are somehow descriptive of your scientific output and importance. And what's good about that, obviously, it vastly oversimplifies. I mean, there's some known problems with some of those numbers, but it also means that our community is capable of latching on to something that is shown to have some correlation with somebody's level of importance. And so somebody's writing GitHub code and it's being forked and people are writing papers and scientific successes are happening because of that. I have some level of belief that we might not know what those metrics are now, but once we start saying this person is a superstar and here are the 12 numbers that show that that's the case, and here's how they're an outlier in that sort of quantifiable way, it's too bad that we can't just go when we're promoting somebody for tenure, for instance, on how they show up, just based on the way people talk about them in letters. In the end, you do need some hard numbers, right? How many papers did you write? What's your H-index, et cetera? And that's just sort of a reality of how promotion happens. But what I was going to sort of voice a worry and maybe ask people if they had the same thing with people in the panel about, kind of working, with different toolkits or different people. I've been doing a lot of machine learning and astronomy, and what you end up seeing is that a lot of what we do can be sort of seen as off the shelf from a machine learning and algorithmic and computational perspective. And that's fine because we're using that as a toolkit in service of novel science. But when we now want to pull in our colleagues or maybe an upcoming postdoc who's from the computer science department and have him or her basically help us out, we then sort of create this infrastructure, this hierarchy where it's somebody doing work in service of somebody else, yet those people also need a way to be rewarded. And what I wound up seeing is that we wound up, in coming up with, data sets that were irregularly sampled. I remember showing in the statistics department that, and then somebody who did machine learning was like, why don't you get data on regular intervals? It's so much easier. And I said, because the sun comes up and there's weather, and they're like, "Wow!" It was like you could see minds being blown because, most people who are working on large-scale problems are really ultimately thinking about monetizing this in the number of ad clicks, right? And so, you give somebody an important novel problem in your science domain, and you hope you can find people who are looking for novel data so that they can build novel algorithms and novel solutions and novel frameworks around those. And the real problem with all of that, of course, is that then it's your job as a domain scientist to come up with something that's novel for you, finding a new type of supernova that no one thought about before, and then also challenge and tax some other part of the infrastructure and make people build new tools that they can then also publish in their trade journals. And this is, I've been thinking about this as sort of the novelty squared problem, right? It's hard to do one thing that's novel, but then reaching across another domain and also having it be novel there is why I think we have a significant challenge of, involving people and rewarding people in other subfields or other parts of our field that isn't traditionally rewarded in academia. So I don't know if people have sort of thoughts on that.
I mean, that has been a big problem for my group, and it's worked out very well, but just through pure luck, we've hit problems where there's an MCMC sampling issue, which is really non-trivial, and there's this astronomy problem that requires it. But it is true that those problems are rare, and this does somehow relate to this question of how you promote people who live at the interface, because they have to be seen, certainly my people who are at the interface have to be seen as creating value in both domains, which is Yeah, I think it's not trivial. Stuart, did you want to say something? We're running out of time, so
Yeah, I mean, I
so
think it was just really
this might
quickly
be last
to,
word.
Oh, I don't know about that. So I guess maybe just a note of caution then, speaking to that, if we think that there's value in having people who are experts at the techniques and the domain in the same place, then we're going to nurture them within the astronomy community. And I think that both of your groups are doing a really good job of that, and I think that's a really positive thing. I think the worrying thing then is that if we don't recognize them properly, the skills that they have are going to get them far larger salaries out in the real world, and once they leave, you've lost all that investment in that dual training. And so I think it's even more important to recognize people like that, because they're so easy to just slip through the net and go off somewhere else.
Certainly, astronomy has a challenge in staying interesting in domains where you can get paid.
Right.
I'm just going to close this. I know lots of people have things to say, but I'm just going to close the session, and we'll continue this conversation over lunch. Let me thank all of my panel members.